GGUF is a model file format commonly used in local inference workflows, especially in llama.cpp-style ecosystems and the tools built around them. When people download a local language model for a desktop, workstation, or home lab, the file they actually run is often a packaged inference file. GGUF helps that runtime understand what the model is, how the data is laid out, and what supporting information is needed to load it. A model file needs more than raw numbers. It needs weights, metadata, tokenizer information, architecture details, context information, and often quantization information. Those pieces let a compatible runtime read the file, allocate memory, prepare prompts text correctly, and generate output. Without structure, the runtime would not know how to interpret the tensors or how to connect the file contents to the model family it expects. It is useful to separate three ideas: architecture, checkpoint, and packaged inference file. Architecture describes the model design, such as how layers and attention are arranged. A checkpoint is a saved set of learned weights for that architecture. A packaged inference file is a runtime-friendly artifact that combines weights and metadata in a format a tool can load. GGUF lives in that packaging layer. GGUF matters because it makes local AI more practical on consumer hardware, used workstations, and private lab machines. It supports model variants that can be loaded by efficient runtimes and matched to available CPU, GPU, RAM, and VRAM. The format does not make every model fast or accurate by itself, but it gives local inference tools a common way to package and read model data reliably. A local model file contains model weights, usually stored as tensors. Tensors are structured arrays of numbers that represent what the model learned during training or fine-tuning. Those numbers are not useful in isolation. The runtime has to know the model architecture, tensor names, tensor shapes, precision, and layout so it can map the file contents into the correct computation. Metadata turns a model file into something a runtime can reason about. It can describe architecture information, context length, tokenizer details, quantization type, special tokens, model family, and sometimes prompt formatting hints. This is why a model file is more than a single blob of numbers. It is a package of data and instructions that helps the runtime load and use the model consistently. Tokenizer data is especially important because models do not process text as raw words. Text is broken into tokens, and generated tokens are converted back into text. The vocabulary, special tokens, and tokenizer behavior need to match what the model expects. If the tokenizer is wrong, prompt text may be represented differently than the model was trained to understand, which can lead to weak or unexpected output. Runtime compatibility depends on both the file and the inference engine. A GGUF file may be valid, but an older runtime might not support a newer architecture, metadata field, or quantization type. Likewise, a runtime may support the architecture but requires specific settings to perform well. Local inference is a combination of model file, runtime capability, hardware fit, and configuration. A typical GGUF workflow starts with choosing or preparing a model file, then selecting a compatible runtime. The file may come from a model repository, a trusted release page, or a conversion process. After download, the runtime loads the file, reads the metadata, allocates memory, and prepares the tokenizer. At that point, the user can test prompts through a command line, web interface, local API, or notebook. Several runtime settings shape the experience. Context length controls how much prompt and conversation history the model can consider. Execution may be CPU only, GPU only for supported layers, or hybrid, where some work is offloaded to the GPU and some remains on the CPU. Thread settings, batch settings, and memory options can affect speed, responsiveness, and stability. These are engineering choices, not just performance trivia. Testing should include more than whether the model answers once. Observe memory use, loading time, prompt processing speed, token generation speed, and output quality for the actual task. A model that works well for short chat may be poor for long document analysis. A quantization that is fast may lose too much quality for careful reasoning. A configuration that fits one machine may fail on another with less RAM or RAM. Documenting the working configuration is part of the workflow. Record the model name, source, file hash if available, quantization, runtime version, context length, GPU offload setting, key parameters, and hardware used. This makes results reproducible and helps compare variants fairly. Without documentation, local AI experiments quickly become a pile of model files and vague memories about what seemed to work. Quantization reduces model size and memory requirements by representing model weights with lower precision. Instead of storing every value with high precision, a quantized model uses a more compact representation. This is one reason local inference is possible on machines that could never load the original full precision checkpoint. Quantization is a practical compression and deployment strategy, but it introduces trade-offs. The obvious benefit is file size. Smaller files are faster to download, take less storage, and require less RAM or RAM to load. They may allow a larger model to run on limited hardware, or allow a usable model to run with a longer context window. For home labs and workstations, quantization can be the difference between a model that only looks interesting and a model that is actually usable. The cost is that lower precision can affect quality, behavior, and sometimes speed. Aggressive quantization may reduce reasoning quality, make outputs less stable, or hurt specialized tasks. Some quantization types are faster on certain hardware and slower on others. Naming patterns can hint at the quantization method and level, but the name alone does not tell you whether it is right for your use case. Smaller is not always better. The right choice depends on hardware limits, expected latency, quality requirements, task type, and whether you value speed or output fidelity more. A highly compressed file may be fine for casual summarization, but weak for code, analysis, or domain-specific tasks. Good practice is to test a few realistic prompts and compare results before settling on a variant. Choosing a GGUF variant means matching model size, parameter count, quantization level, hardware capacity, and workload. Parameter count gives a rough sense of model scale, but it does not automatically determine quality for every task. A smaller well-matched model can be more useful than a larger model that barely fits, runs slowly, or forces you into a context length that is too short for your workflow. RAM and RAM are practical constraints. CPU-only inference may work with enough system memory, but generation can be slower. GPU offload can improve performance when enough RAM is available, but the amount of offload depends on the model, quantization, context length, and runtime settings. Hybrid execution is common on consumer machines, where the user balances what fits on the GPU with what can run acceptably on the CPU. Context length should be chosen based on the task. Long context can help with document review, multi-turn conversations, and retrieval workflows, but it consumes memory and may slow prompt processing. If your work uses short prompts, a very large context window may not be worth the cost. If your work involves long reports or code bases, context can become a core requirement rather than a luxury. Avoid random downloads without understanding trade-offs. Prefer trusted sources, read model cards, compare quantization variants, and keep notes on what you tested. Consider latency, throughput, quality expectations, license terms, and whether the model fits the problem. The best GGUF variant is not the biggest or smallest file. It is the one that runs reliably on your hardware and produces acceptable results for the job. Tokenizer compatibility matters because the model was trained to interpret text through a specific tokenization process. Special tokens may mark the beginning of text, user messages, assistant messages, system prompts, or stop conditions. If those tokens are missing or misused, the model may still generate text, but it may not follow instructions in the way the user expects. Chat templates define how conversational prompts are formatted for a model. Two models may both support chat, but one may expect a system message in a particular structure while another expects different role markers or separators. A web UI or runtime may apply the template automatically, but users should still understand the concept. Prompt formatting is part of model compatibility, not just interface style. Incorrect formatting can produce weak, oddly structured, or less aligned output. The model may ignore a system instruction, continue a user message instead of answering, include unnecessary role labels, or stop too early. These issues can look like model quality problems when the real cause is configuration. Before blaming a model, verify that the runtime is using the right tokenizer, chat template, stop tokens, and context settings. Metadata helps runtimes load and use models correctly by carrying facts that would otherwise need to be supplied manually. It can identify architecture, tokenizer configuration, quantization information, and sometimes prompt-related settings. Metadata does not remove the need for testing, but it reduces guesswork and makes local inference workflows more portable across compatible tools. Performance issues in local inference often fall into two categories: slow prompt processing and slow generation. Prompt processing is the work of reading and embedding the input context. Generation is the token-by-token output step. A setup may load quickly but generate slowly, or handle short prompts well but struggle with long context. Knowing which phase is slow helps narrow the cause. Memory pressure is one of the most common problems. A model, quantization, or context length may exceed available RAM or system RAM. GPU offload settings may be too aggressive, causing failures or instability. CPU-only execution may work but feel slow. Disk speed can affect model loading time, especially with large files. Batch size and thread settings can help, but they should be adjusted carefully and tested with the actual workload. Sampling settings affect output behavior and can be mistaken for performance or model quality issues. Temperature, top P, repetition controls, and related options influence how deterministic or varied the output feels. If results seem rambling, repetitive, or inconsistent, the issue may be sampling configuration, prompt formatting, model fit, or quantization quality. Troubleshooting should separate runtime settings from model capability. A practical troubleshooting loop starts with a known compatible runtime, a trusted model file, conservative context length, and a documented baseline. Then change one variable at a time: quantization, GPU offload, thread count, context length, or sampling settings. Compare memory use, speed, and output quality. This disciplined approach is slower than random tweaking, but it produces knowledge you can reuse. Downloaded model files should be treated as supply chain artifacts. Provenance matters because unknown sources can create trust, licensing, integrity, or safety concerns. Prefer model files from reputable repositories, maintainers, or organizations. Read model cards and release notes when they are available. Understand whether the file is an official release, a community conversion, a fine-tune, or an unknown repackaging. File integrity checks help confirm that the file you have matches the expected version. Hashes and checksums do not prove that a model is good or safe, but they can detect accidental corruption or unexpected modification after download. When a trusted source publishes hashes, record them with your local notes. This is especially useful when moving model files between machines or rebuilding a lab. Licensing needs real attention. Model licenses may affect use, redistribution, modification, commercial deployment, attribution, or acceptable use. A model that is fine for personal experimentation may not be allowed in a client environment or product. Local execution does not erase license obligations. Reviewing the license before building workflows around a model prevents painful surprises later. Local inference can improve privacy because prompts and outputs do not automatically leave your machine. That benefit depends on the surrounding workflow. Logs, dashboards, synced folders, screenshots, notebooks, and shared drives can still expose sensitive data. Treat models, prompts, outputs, and runtime configuration with the same care you would apply to any other data handling system. GGUF packages local model data and metadata so compatible runtimes can load models efficiently. It is commonly used in local inference workflows where users want to run language models on desktops, consumer GPUs, workstations, or home lab systems. The format helps organize weights, tensors, tokenizer information, architecture details, quantization data, and other runtime readable metadata. Effective GGUF use requires more than downloading a file. You need to choose the right model variant, understand quantization trade-offs, match hardware to workload, and test settings against realistic tasks. RAM, VRAM, context length, CPU and GPU execution, prompt formatting, tokenizer compatibility, and sampling choices can all affect whether a model feels useful or frustrating. Strong practice also includes preserving provenance, checking file integrity when hashes are available, reviewing licenses, and documenting runtime settings. Model files are part of a software supply chain. They should be tracked with the same seriousness as other important dependencies, especially when they are used with sensitive prompts, private documents, or production-adjacent workflows. The goal is not to collect the largest number of GGUF files. The goal is to run appropriate models reliably, privately, and repeatably on available hardware. A well-managed local inference workflow makes model source, file choice, runtime settings, and performance trade-offs visible. That visibility is what turns experimentation into a dependable technical practice.